All right. Cool, so let's get started. So today we wanted to dive into something reasonably concrete finally. So this is a paper called SibylFS. And the reason that we wanted to read this is sort of several-fold. One cool thing going on here is that these guys actually go through and formalize a pretty sophisticated system. Some kind of serious system, in their case, file system. But they don't actually cut too many corners. They really specify file systems as they exist today, for the most part. And they take their inspiration from the specification called POSIX that we'll look at in this lecture. It's an interesting experience to see what does it take to really formalize something that already exists and has all these interesting aspects to it. And there's a number of tricky cases they run into. Another sort of cool thing going on here is they actually show you what are the cool things you can do once you have a formal spec. So once you've specified a file system, they actually show that it can be actually a pretty powerful technique for testing a file system implementation, which can potentially catch more issues than other techniques that people have tried before the SibylFS idea or artifact came around. And others actually have this interesting idea of actually spec invariance. We'll see this come up later in other papers as well, but they basically check that the spec itself is internally consistent with some rules that you might expect out of it. Another sort of reason, maybe almost like an impact thing, is these guys actually influence POSIX. So we'll talk about POSIX in a bit, but POSIX is this reasonably impactful specification. It's been around for a while. And as a result of this work on SibylFS, the POSIX specification experts actually went ahead and changed their spec a bit. Not in dramatic ways, perhaps, not like SibylFS is the POSIX spec now, but certainly there's issues that got fixed in the POSIX specification as a result of this work. And the big challenge that these guys really worry about in this paper is really non-determinism. So non-determinism is sort of the source of some of their performance challenges, as well as figuring out how to correctly specify the non-deterministic behavior of the system. So this is really the interesting part, in some sense, intellectually tricky business. So one thing that we asked you guys to think about for the paper, for the reading question, and I'd like you guys to like go do a breakout and sort of figure out what the answer is so what's the non-determinism in the spec? What kinds of non-determinism are they modeling? And why is it valuable to have this non-determinism in the specification? So why is it there? What does it enable? If you didn't have this non-determinism, would you catch fewer bugs or what? What's the deal? So we'll do a quick breakout group, 10-ish minutes as usual. Any questions before we jump in and talk about that? All right, so feel free to come back to this room, I think, whenever you guys are done. All right, so it looks like everyone's back. So what did you guys decide? What's the non-determinism in the specification?
So
yeah, go ahead.
Yeah, sure. So there's a few examples that they list on page 42 of the reading. But basically, like one of the examples is if there's several distinct errors that could happen, the what's actually returned is determined by the order of like how the file system checks those errors. Mm-hmm. And that's totally up to the implementation of the file system. And so basically the SibylFS allows any of those like orderings to happen. And so like the ability that this gives people is that when you're using SibylFS, you don't have to adapt to like if it didn't use the non-determinism, it would only accept one form of the ordering. So you would either have to like you wouldn't be able to use SibylFS, or you'd have to adapt your file system to use that ordering, or you'd have to change SibylFS to use your ordering.
Yeah, so I think basically what you're saying is like, yeah, so many possible possible errors, okay? In some situation, so if you're trying to do some operation that's not allowed for maybe one reason or multiple reasons, the spec says, well, you know, you could get this error, that error, either one's okay. And I think what you're saying is, in general, sort of non-determinism basically means can check many implementations. So so that's sort of a broad category for why this is an important non-determinism to capture. Same spec, many file systems all fall under the same specification, and the choice here probably is so the choice is made by the file system developer. They just decide, well, I'll return this code or I'll check this thing first. Yeah, makes sense.
And an interesting thing that this brings up that we were talking a little bit about is that like SibylFS won't necessarily tell that, or at least we don't think based on the paper that it doesn't really care about whether or not the file system is consistent with the order it chooses for an example like this. So because it allows you to use whatever ordering, if like one certain implementation of the file system has like a certain error that's supposed to come first all the time, but then something happens where the order is flipped or something, SibylFS will say that's okay because it allows any ordering.
Yeah, so maybe it's 2 lakhs. I don't know if it's 2 lakhs or not, but what I think you're saying is the paper spells out this error case as well. You know, you could have returned E permission first, or E doesn't exist, or E is a directory, and they're thinking, well, you probably should have checked this first, this second, and this third, or the other way around. And you're saying, well, you know, it could be a crazy implementation out there that like sometimes checks this thing, sometimes checks this other thing, returns either one, and then the spec will say that's totally fine. And in some sense, the spec is right, but there's something funny going on, perhaps. Yeah, so that's a good point. Yeah, so there's quite a bit allowed by the spec that you probably wouldn't expect any one implementation to exercise the whole spec, to like take advantage of all this non-determinism in every possible way. I don't think they're aiming for this as the goal. And usually it's not the goal of any spec, yeah. That's a good observation, yeah. Other non-determinism sort of sources? So I guess I think you got a good pointer to like basically that table on page 42 from the paper, right? So the other thing they talk about is so this number of bytes returned by read. So how important is this? Actually, one question is, where is the non-determinism coming from? Why is there a different number of bytes being returned? Any of you guys figure out sort of what would go wrong, for example? I guess that, well, one sort of easy answer is like, this would go wrong always. If you have not enough non-determinism, the thing that goes wrong is that you can check all the implementations that might return different values. So maybe one question more concretely is, why are implementations returning different numbers of bytes from a file read? Anyone wanna, did you guys discuss this or try to figure out what's going on here?
It's probably faster to just return a few bytes rather than return the...
Yeah, so one possibility is sort of performance choices. So it might be that some file system implementations decide they will do one page at a time, or maybe they grab one lock. And if they have fine-grained locking of some kind, perhaps they'll grab a lock, return as much as is there, and then return that to the application. Another possibility might be that if a part of the file maybe is cached in memory, maybe the implementation will decide, well, you know, I'll return the part that's cached in memory, and I'm not going to bother waiting for the other part from disk to go in because there is something to return now. Maybe that'll be enough for the application. There's many sort of choices that you could imagine happening in the implementation that give rise to this artifact of returning different numbers of bytes from a read sys call. Now, it's not super clear whether how broadly implementations actually take advantage of this. I think for file systems in particular, often implementations try to read the full buffer size that are requested by the application. But you could imagine, but I think POSIX, strictly speaking, does allow a little bit of flexibility here, and the SibylFS model tries to capture that. And so these kinds of non-determinism that we've talked about here are sort of more, I don't know, sort of implementation choice business. The developer just decides, well, I'm going to return this error code, or I'm going to have this plan for a number of bytes from read. Then they talk about readdir, which is quite a different example in terms of what happens. So readdir is the system call that allows you to read the contents of a directory. And the problem with this guy is that it's just, well, not atomic and highly under constrained by the spec. So in order to read a directory, you go through many steps. You go one element, second element, third element, roughly speaking, from a directory. And the spec doesn't really say what order you're supposed to get them in. So the spec very explicitly gives quite a bit of freedom here. And this readdir operation doesn't happen at one point. It happens over many steps. So readdir and concurrency together are probably a slightly different source of non-determinism here, where the execution might actually differ quite a bit because of other threads running and dynamic decisions at the implementation's execution time that give rise to potentially different outcomes. So I think that's roughly what the paper sort of argues are the big sources that they're capturing. Does that make sense? Anyone else sort of had questions or comments or interesting observations about this stuff that you guys want to talk about? All right, so I think this is roughly indeed the sort of set of non-determinism captured, right? So let's try to talk about this paper. So I want to first back up and maybe set the context for how would you test a file system even before the SibylFS came out? So there's this POSIX specification that the paper refers to, but doesn't really explain in as much detail. So POSIX is effectively the Unix specification, if you will, and tries to sort of cover the common aspects of Unix-like systems. And it's not a particularly formal spec in the sense of this paper, so they don't have a precise model in this DSL or anything like this. You can sort of think of it as these manual pages describing what the developer should expect from each function call that's covered by the POSIX specification. And it covers the typical sort of libc interface, if you will, or maybe a closer to a syscall interface on a Unix-like system. And where this POSIX spec came out from is that in the 1980s, there was a sort of a blooming, field of various different variants of Unix operating systems. And they looked quite similar, partly because of their heritage. Many of them came from the Bell Labs version of Unix or the Berkeley version of Unix. So they all looked quite similar at the core, but there were annoying differences, minor diffs between them, and sometimes maybe not even so minor. And this made it kind of cumbersome or hard for developers to write software that would run on all these variants of Unix. And it's super appealing because it feels like it's the same roughly operating system, it's Unix. But then just like the syscalls are a little bit different, the error codes are different, the corner cases are handled differently. And the other thing that was going on in the 80s was that actually many of these operating systems were closed source. So in contrast to how things are today, you can't just, like today, I would just pull up the source code of Linux and figure out what's going on. So if I want to understand what happens in this corner case, worst case, I can read the kernel source code and see what it does. And there's basically Linux is the main competitor in the space that's left. On the other hand, back then, there were many different operating systems, all closed source, so it was hard to figure out what is going on. So the goal was to figure out a common spec that would allow portable applications to actually run or compile on all these different variants of Unix. So what happened was that there was a sort of a group of experts that got together from all the different Unix vendors. And they got together and decided to figure out what is the specification that their Unix operating systems should follow. As you can imagine, these guys represented sort of large existing code bases. None of them really were too excited about super changing their implementation to fit some hypothetical new specification. So the outcome of this was more that they codified formalized, or maybe not formalized, but specified the common core. So instead of, there was some effect of this POSIX standardization effort that actually caused some of these operating systems to change their behavior and become a little bit more standards compliant or consistent. But for the most part, I think this POSIX specification was really a formulation or a distillation of what is the common thing that runs the same way in all these Unix operating systems. And it actually left quite a bit of room for each operating system to be different. So all the various features or interesting tidbits that each operating system had, to a large degree stayed as choices or non-determinism in this common spec. Make sense? Any questions about how this thing came about? That's kind of an interesting historical artifact. For all the, things I'm saying that, like, maybe it could have been better, it was actually pretty influential, right? So still, you see these common man pages or manual descriptions of what the API is being widely referenced and used. Linux certainly looks at POSIX quite a bit or tries to capture what POSIX says. Not 100% of the time. Sometimes they disagree on what should happen, but it's a pretty influential specification in the field of sort of figuring out how to spec an interface. All right, so in this context, this paper in particular tries to tackle the problem of trying to figure out if your file system implementation is correct. And POSIX, of course, has some spec for this. So the question is, how might you go about testing your implementation and figure out if it follows the spec or not? So inevitably, what people do is they run some kind of a workload on your implementation. So you got some file system like Linux, ext3, or macOS, or FreeBSD. These are the things that at least this paper talks about. So you need some kind of a workload. And this is actually pretty widely done in practice today. You want to test a file system, you cook up some way to push the file system around. And you really try to push it in various ways. So you might have a workload that really tries to push large files and create lots of large files and do I/O on them. Maybe you can have many files, so like many small files in your file system. Or you worry a lot about concurrent operations. And you have lots of threads doing lots of things at the same time in the file system. Or maybe you even figure out some way to stress crashing. So you have some workload and you keep crashing the file system and seeing what happens afterwards. So the way to sort of visualize it in the way we've been describing systems is you've got some state, and the workload is going to force the file system implementation to step through lots and lots of states and produce some resulting state. And now the question is, so you got this great workload, push the file system around, the file system did something. The question is this correct? And this is where there isn't really a great answer today. And this is partly what this paper is trying to answer. So today, the reason why there's not a great answer, and part of the big sort of angle of this that the paper is trying to capture is that really the file system behavior is actually quite complex. So it's actually a little bit hard to tell whether a file system did something right, because actually, there's lots of moving parts, and there's many things that a file system could be expected to do, depending on the details of what each system call was intended to perform. And moreover, it's not just complicated, but actually sort of different by the implementation. So this is the non-determinism part of it. So it might be a little bit hard to figure out what correctness even means. And these small differences due to non-determinism can sort of amplify themselves. So you ran some workload, and it might be that one of the system calls here was non-deterministic, and you thought it was going to go one way, and the implementation actually chose another legitimate way to implement that syscall. from that point on, the whole execution could like diverge out to a very different state because of small differences in how one syscall executed. So all these sources of non-determinism can amplify into big results for any particular workload, which makes it difficult to figure out if something was right or not. And the POSIX spec, which we've talked about just now, it's a little bit informal. So it's a bunch of English prose. So if you wanted to look at one of these traces, sort of an execution produced by a workload, maybe you could sit down with a POSIX book and, you know, scratch your head for a while, trying to figure out, well, this looks okay, maybe there's a problem here. It's a highly tedious thing because this is just a bunch of English prose. It's not an executable thing or a test harness that you could use to decide whether a spec is right. So in absence of really a precise definition of what it means to be correct, sort of two placeholders that people have used in practice. One is to do basically what we saw in the static analysis papers last lecture, which is to aim for a very low bar of what correctness means. So roughly, many of these test cases just say, you know, no kernel panics. Or basically, if your workload causes your file system to reboot your computer or run out of memory or divide by 0 or do something else, that's bad. Maybe not, maybe there's other bad things going on, but if the kernel panics, you know something has gone wrong. So it's sort of a very loose boundary of what's acceptable or not acceptable in this case in terms of behavior. And I should say, actually, it's been an extremely effective testing practice, partly because file systems tend to have a number of consistency checks in their runtime implementations. So you do get kernel panics, you know, in many cases when the file system has done something wrong, but it's not complete. And the other sort of placeholder that people have figured out is to look at application behavior. So the way to think of this is basically take some popular app, and the popular application had a developer that had some mental model in mind of what the file system should be doing, and they wrote the application to expect the file system to behave correctly. And as long as this popular app is reasonably correct, what you can do is run the popular app on top of your file system. And maybe the popular app is generating the workload at that point. And the popular app might crash or report an error if the file system does something unexpected. So the correctness definition here, roughly speaking, is popular applications running on this file system should not crash or should not, you know, error out in some sense. That makes sense? It's a fairly loose specification as well, and sort of assumes that popular applications have the correct model of file system behavior, but it's a very effective one. In some sense, it's the end-to-end measure, because this is what your users are going to expect to work correctly. And the story Butler tells is that indeed, I think Microsoft uses this, and Intel use this kind of specification as well. So, you know, new Intel processors are part of their definition of correctness is that it can boot up Windows. And that is sort of a pretty good specification in some ways. The Windows developers have carefully written their code to expect the right behavior from the processor. If the processor cannot boot Windows, probably something has gone wrong, even if their, you know, semi-formal specification says everything is correct. So this is an important, so these sort of two, you know, definitions of correctness are relatively easy to realize and pretty effective in practice. But this paper is trying to aim a little bit higher, or a little bit more principled perhaps, to basically decide whether we saw some misbehavior in this executable trace produced by a workload, independent of, you know, maybe this is not causing a kernel panic, but something else has gone wrong, and independent of requiring some application to trigger an error by observing a bad behavior from a file system. Does that make sense? Any questions so far about this? All right. So maybe let's now take a look at sort of a rough sketch of what this SibylFS system looks like. So as we were talking about, at the bottom of the stack, roughly speaking, is some kind of a file system implementation for them. So this might be Linux, ext3, or whatever else in macOS, or who knows what. And what they're going to do is cook up a workload. And this workload is going to be used to drive this file system implementation. And as a result of the workload, we're going to cause the file system implementation to transition through a whole bunch of states, like I was drawing on the previous slide. And this transition sequence is going to be annotated by this SibylFS tool to reflect what operation happened at each one of these transitions. So the way they annotate this is that they have basically labels on these arrows, which is one of the ways that Butler was presenting how to think of state machines and their correctness. So here you might have a system call like rename file A to B, and here you might have another transition that says, well, this guy returned, and these transitions are indexed by the process ID that is invoking the operation. So here it might be process ID 2 invokes the rename, and here the second process returned OK, and here another transition, create in process ID 3 file X, and here maybe you'll get an error saying E exist. There's already a file X, can't create it a second time. So this is the kind of thing that comes out from the file system implementation running our workload here. And then the question is, so very much like in our refinement diagrams, our question is, does this execution of the code at the bottom level correspond to one of the allowed executions of the spec? So if you remember, our sort of definition of system correctness was that the trace produced by the implementation, which is the list of these roughly transitions, rename, return OK, create, return exist. This trace must be a subset of the allowed behaviors of the spec. So the question is, what the heck does a spec look like? So here we have the code. How do we think of the spec? This is where their main contribution comes in. They're going to actually write a specification, which is to say define the set of possible executions at this level, and then check whether the particular execution they observe from the implementation is a subset of all the executions allowed by their spec. And roughly the way the spec works is that they want to operate on the system in a black box way. So they don't want to look inside of the implementation details. The only thing they see are the system call invocations and the results. They don't know actually what the state of the file system is. They only can indirectly infer it based on the return values of various system calls. So the way they're going to sort of run their spec along is that they initialize it to some kind of initial state over here. And at the start, this is basically the only time they know what the state of the file system is. When they start the workload, they are going to know that we started in an empty file system, or maybe in a specific file system that contains 2 files, or something else very concrete. So they're going to establish basically this abstraction relation. It's not formalized in the way that we've been talking about it, but there's a connection between the code state and the spec state at the outset, because we know how we started our workload. And from that point on, the only thing that's going to happen is that we're going to take our spec state that describes where the file system was to begin with, and we're going to look at all the possible transitions that could happen. So here, we might also execute the rename transition from A to B at the spec level and get into some state. And then maybe there's actually multiple transitions that can happen here according to a spec. Maybe the file system can do something internal. So we'll talk about these guys. These guys have a notion of a tau transition, which basically says actually no label happened. The file system just did something locally and didn't return or take any calls. Or maybe we immediately return an error. So okay, maybe here an error is the file system is read-only. You can't rename stuff. Another transition might be after 2 internal steps, you have another return. Okay, and so on. And there's this sort of branching structure that describes all the possible executions from this starting state. And the question of SibylFS is to basically figure out whether the concrete execution they got at the bottom here is somewhere in this giant tree of all the possible executions that the spec describes. So you can imagine this is going to be kind of a large tree, and every time you have a syscall, you might sort of branch again, and if you were to materialize this whole tree, this would be a bit of a crazy performance problem. But they actually have a number of tricks to actually make this fly surprisingly well. So they're able to check quite a number of tests in a reasonable amount of time. Does it make sense? Any questions on this overview of how their system is going to work, or what the tricky parts are? All right, so there's sort of two interesting tidbits here that I wanted to briefly mention. One is this workload business. So we got to cook up some kind of a workload. And for them, the really cool thing is that the workload just needs to drive the file system into interesting corner cases. So they need to force the implementation to exhibit behaviors that might be tricky for developers of the file system to get right. And hopefully, if we drive them into those corner cases, we'll get the implementation to show a bad behavior. And then we can say, well, that's a bad behavior. We should fix this bug to the file system developer. But the really cool thing is that the workload just needs to drive the file system into the corner case. So there's actually no need to know, no sort of expected result here. So the workload just needs to push the file system. It doesn't actually have to say what should happen when the file system is pushed this way. Because this oracle, this question over here, that's going to answer the question of whether this file system did something right in that corner case. But the workload's job is just to force this case to happen. As a result, they can actually do quite a bit of automated workload generation. So they have this test generator that basically explores almost like all possible syscalls. And as a result, they get actually pretty good coverage because they can test a lot of different situations that could happen in a file system. And more manually constructed test suites typically have to say what they expect the result to be. So for crazy combinations of syscalls, the test author might not even know exactly what to expect, so they don't write these crazy tests. But in their case, they can drive the file system into all kinds of crazy behaviors. So that's pretty cool. And of course, it's not all fully generated. They also do some manually generated test cases too for things that turn out to be hard to fully explore through their test gen. But nonetheless, a really cool idea to split the pushing of the file system into corner cases from the question of did the file system do the right thing when pushed there. So that's one cool thing about this. The other is basically the SibylFS model, which is the basically question of how do you actually implement this tree? How do you describe this giant tree of possible executions at the spec level? So for this, their plan is to actually use a special language called LEM. This is a domain-specific language, or DSL, that was written by one of the co-authors of this paper, Peter Sewell. And he's used it with his colleagues for describing all kinds of precise specs for various systems. But it's a pretty nice language for writing specifications. As a result, it doesn't need to be sort of super efficient or super necessarily even executable in all cases. But in this case, they actually managed to make it executable enough to produce the right sort of part of this tree to check the spec. And the basic plan there is that in this language, they're going to define what is this abstract state inside of one of these squares that I've been drawing. And then they also use this language to define the transition. And this transition is basically this arrow between squares that I've been drawing over here. So they have this language to precisely pin down what is a square, what is an arrow, when are arrows allowed, and what are the labels that go with the arrows. So these are the sort of main components of the system. Hopefully it makes some sense, or maybe a slightly different way of looking at this diagram than what the paper presents. Any questions so far? Anything unclear you want to talk about? All right. So let's jump into how these guys are handling non-determinism, which I think is the sort of the big thing here. And just to remind you, like what we're going to try to figure out is how are they dealing with the branching structure of this tree? How are they describing the possible branches, and how are they checking whether a concrete execution is in one of these branches? All right, so non-determinism. So one angle that we could take on this is to figure out how are they going to describe this possible executions in the spec. And for that, in their DSL, this LEM DSL, they're basically going to enumerate all the possible states. So in the paper, they talk about this thing called next state enumeration. And the way to think of this is that you might be in one particular state, and they're going to define a transition function, a transition relation, that is going to say, well, from this possible state, there's a number of things that could happen. So for instance, if you want to describe that many error codes could be returned for a single syscall, we might say, well, from this state, it's actually okay to return E exists. And also it's okay to return E is dir. So this is maybe an operation that's trying to act on a file, but it turns out to be a directory. And maybe it's trying to move something into it, but there's already a thing in that directory. I don't know, I'm just sort of making up a situation here. But you might imagine you want to describe many possible error codes, and this is what it would look like in this state transition diagram, where from the starting state, the result of some system call that has already happened in the square is that we return either one of these codes to the application. And in order to make it convenient for the spec writer to pin this down, they actually have a fairly nice construct in their domain-specific language in this LEM thing, which is they have this triple pipe operator. So they can say basically either A or B, where A might be something like return E exist, and B might be this statement to return E is dir. This is not exactly literally the correct LEM syntax for this, but the cool thing is that in LEM you can use this triple pipe operator, and then that tells the DSL that either thing is okay. So you can either return E exist or triple pipe return E is dir. And that describes this kind of a state transition diagram drawn on the slide. That make sense? So that's the way that they describe non-determinism in their transition function. And then on top of it, what you can see is actually like if you have ever had one state, then all of a sudden you might say, well, what's next? The answer is here's two possible things that are next, or three, or a large number are next. And as a result, you might not even have a single starting state. You might have multiple starting states. So here, they have this notion of sort of tracking many possible states. So as we were seeing on the previous diagram, you might branch out and go into many possible states. So at any given point, we don't actually know what the abstraction relation is. So here I'll sort of draw it maybe with a dotted line. We don't actually know what is the correspondence here and even which pair of states are connected by the abstraction relation. As far as we know, all we can see are the transitions, these labels that are generated by the code and that are generated by the spec. So we don't actually know which states correspond to each other. Consequently, there's a bit of an uncertainty at any given point at the code level, which state at the spec level corresponds to it. So SibylFS actually maintains multiple possible states at the spec level that could correspond to the current state of the file system as it executes some workload. And as a result, here might be our combination of maybe three possible states at some instant. And we want to know, we were in this state, we did something at the implementation level, where did we go? And the way this is going to happen is we're going to take every possible state that we think might correspond to the current concrete execution, and then we'll apply our transition function to this. So maybe from this state, the transition function says, oh, you can get actually 3 states. I don't know, A, B, C. And here we go, 3 possible states. This guy maybe goes to 1 possible state, D. Maybe that's the label that we get. This guy, maybe this one actually goes nowhere. A possible option in their system is that in some state, maybe there is no next transition. Maybe you've gotten into some dead-end state and there's nowhere to go. So maybe not all states are evolvable in this sense. And then here's the next set of states. So basically you went from being in one of these 3 possible states to being in one of these 4 possible states. And here's the labels that you generated along with the transition. That makes sense? So this is sort of the way that their execution system is tracking the state of the, this is how their model tracks the state of the real implementation. They have this uncertainty, but they maintain, well, you know, it could be one of these 3 possible things. Let's see where we go from there. You know, maybe it expands or contracts depending on what actually happens. Questions about this? Makes sense to some extent? So a big problem you might expect in this situation is state explosion. What I mean by state explosion is that you could generate a very large number of states. So if there's non-determinism in many of these transitions, every state goes to 2 or 3 states and then goes to 2 or more states at the next level. So you quickly get an exponential number of states. So one question is, why doesn't this happen? What causes them to shrink the number of states so it doesn't grow out of control? Any guesses? Try to pick on some people otherwise. Kevin, any thoughts?
Yeah. Would it be because some of the states, then when you try and do another transition, is an invalid transition, so then you can cut off that entire branch?
Yeah, okay, so that's certainly one of them. So like this situation, that's pretty cool. The whole state went away and stopped branching. That really helped us avoid some of the explosion. So certainly, yeah. So like one thing is dead-end states could be an answer. I think this happens sometimes for them, but I don't think it's well. It's hard to judge which thing is sort of the big win for them. But I think they don't have too many of these dead-end states, as it turns out. Any other thoughts? How do they prune this? Any guesses? I'll pick on Amanda, if you're around. What do you think? Maybe not. All right. So I think the other thing that's going on is that they actually try very aggressively to match labels with the implementation execution or the implementation trace. So the thing that really, I think, the other sort of dimension of what causes them to constrain this state explosion is that they can require that the labels on these transitions, like this A, B, or C thing here, they must match the actual trace produced by the code. And if the labels don't match, there's no need to continue executing, because like even if we continue executing that state, it's not going to match. It's already mismatched. So it will keep mismatching all the time in the future. So as soon as the labels are mismatched, then we know this is not a possible spec transition history that describes how the code really ran. So maybe it was B. We know that A and C are not it, so we can stop considering these guys. Maybe this transition was also B, in which case, well, we can keep both of them around. So I think the labels on the real execution are the big reason why they actually don't have crazy state explosion problems. And there's sort of one other cool thing, which is that if there's 0 matching labels, that's how they actually know they have a bug. well, I don't know, bug or inconsistency. So the way they know that the implementation just does not match the spec as is if there are no valid states here that have the matching label. So we use this rule to prune out the transitions at the spec level that don't match what we saw in the real syscall arguments. And if we pruned everything, then we know that the spec and the implementation just diverge. There's no possibility that they're talking about the same execution. Make sense? One interesting thing, actually, the paper mentions a related project, prior project by this overlapping set of authors on trying to formalize the TCP specification for the network protocol. And there, they actually cite numbers that are way, way higher in terms of how long it takes them to check for consistency between the implementation and the spec. And I think part of the thing that's going on, we were speculating before lecture started here, is that I think in a file system, you find out pretty quickly what happened, because you might issue a syscall, and once you issue the syscall, maybe there's some uncertainty as to what happened. Did that syscall actually change the state? Did it return an error? Which error? Etc. But almost the next thing that's going to happen is that you're going to get a return value from the file system, and that sort of pins down, did it happen or was there an error? And if there, then which error? So you very quickly you expand when you issue a syscall, and almost immediately you collapse back down after you get the return value, and you figure out what happened. In contrast, in something like a network protocol like TCP, there's a lot of uncertainty that's going on in the network, and you might not actually get the answer to what really happened until much, much later when you've retransmitted and you've timed out, and finally you get an error saying your packet's lost, or you should assume that it's lost. So I think the time to collapse of uncertainty is much quicker in a file system than a large distributed system or a network system like TCP. And as a result, they're able to keep their state count under control much better here. That make sense? All right, so this is sort of an overall sketch of what their plan is for dealing with many states. And you could imagine here's how they sort of deal with many error codes. They just have this triple pipe combinator that describes all the possible errors that you might return at one point. So that's one kind of non-determinism they have. The other example that's much more interesting to look at in some ways is this read-dir operation. So read-dir, just to give you some context, the way you list the files in a directory in a POSIX system is first you call open-dir, and this gives you a handle or a file descriptor, some kind of a object that you can then use to read out the elements in that directory one at a time, or a small batch at a time. So you call open-dir, then you call read-dir, you get a couple of file names back, then you call read-dir again, you get a couple of more file names back, and so on, until read-dir says, that's it, there's nothing else I can list for you, at which point you just close it up and call close-dir. So this is how a POSIX system expects that you list the contents of a directory, and it's actually quite non-deterministic, sort of for two reasons. One thing going on is that POSIX basically sort of allows any order of files. So if you have a directory that contains files A and B, then it's totally okay for this reader call to return A and this guy to return B. And it's also okay if the first guy returns B and the second one returns A. Or it's also okay if the first one returns A and B together and the second one says end of file, nothing else to return. There's lots of choices that an implementation is allowed to make for how to list the contents of a directory. There's no sorted list, order of a directory required by the syscall API. The other source of complication in read-dir has to do with concurrent operations. So you might have concurrent creates or deletes in the same directory. So here's a question, right? Like you called open-dir, then you called read-dir, and you got some file out of the directory, but not all of them. That's one system call. In the meantime, some other process could sneak in and right here between the two read-dir calls, and it might actually create a new file or delete a file. The question now is, what should this read-dir return? Because the directory was modified sort of underneath of you. It's not entirely clear what should be the right spec here. So what do these guys do actually? So the SibylFS guys basically try to reason about it in terms of some constraints. That's one way to think of it. So one example is, suppose you had some file in a directory that was just unmodified. So if you had an unmodified file in a directory, and what I mean by unmodified is that for the whole duration of this sequence of open dir, read dir, all the way to the close dir, if that file was not created or deleted or touched in that way, then, well, probably a reasonable spec is it actually must appear in the results of read dir. That'd be cool. But if you had a file that was concurrently deleted, well, then the answer is, you know, may appear. It's okay if it shows up. So for example, here, if we had this create or delete, if this guy deleted A, then actually it's okay. If we saw A and then it was concurrently deleted, it doesn't seem too bad because we saw it and then it got deleted and all right. But then if we saw B first and then A got deleted, might still be okay for us to see A because the reader implementation buffered the result. It already sort of saw that A existed ahead of time at the open dir time and saved it for us. Alternatively, it might also be okay if this actually says EOF. We saw B and then we don't see anything anymore because A got deleted. So either behavior might be okay. That make sense? Questions about this? You can imagine similarly for concurrent create. So if a file was concurrently created, similarly, may be okay for it to appear in the result of reader, but also not a disaster or allowed by the spec to not appear in the result of reader with concurrent creates.
It might be worth pointing out that you might have seen something like this in a programming language where when you iterate over a list, you're not allowed to concurrently modify that list, right? So something like Python, actually, I'm not rightly sure what happens if you try modifying the list while you're doing an iteration over it. In those languages, it's okay for the language to just say, you can't do that, the program will crash if you try to do that. But it's not okay for the file system to make the same guarantee that your kernel crashes if you try to concurrently modify a directory while reading it.
Yeah,
so
there's a certain
out all of this
mindset,
stuff in some way.
Yeah, so there's a certain mindset I think that comes along with a file system, which Tej correctly points out. In a programming language, it's fine to say, okay, so like, for example, in Go or some other programming language that has native objects like maps or lists, an alternative answer might have been to say, this is undefined behavior. This would have been the choice of C developers probably, if they had a list or map primitive in their language, to say, well, you can't concurrently operate on these things, and anything could happen. At this point, you know, almost doesn't matter what the implementation does. It's justified in doing anything it wants. But in a file system, right, it would be crazy, as Tej points out, for the file system to crash because you were reading a directory at the same time as you were creating files, and that would be unacceptable. You don't want an application to be able to crash the kernel.
Well, it's a little more subtle than that, because you could have said, no, the kernel isn't going to crash, but it's going to return an error. That wouldn't be a good idea either, but for somewhat more subtle reasons.
Fair enough, yeah. So this may be an oversimplification of the sort of justifications here, yeah. But there are sort of reasonable workloads where you might expect you know, concurrent. I guess where it's coming from is that there's I think a mindset in the developers of these file systems. They're expecting certain applications to use the file system in some way. You might have shell scripts running or listing files, and concurrently other processes are creating, deleting stuff. And there's sort of an expectation that it works in a certain, you know, sensible way. I guess captured by POSIX in some way, but yeah, would be hard to write applications if they were returning errors in their concurrent reader.
Well, I think the more serious problem in this particular case is you wouldn't, if I do a read dir and then I start pulling entries out one by one, how do you know when I'm done? You wouldn't know when to stop giving the error and allow changes to the directory.
Yeah, I suppose, right. So I guess that maybe you're thinking the Windows model is you actually lock up the file or directory when you're operating on it. And if the reader grabbed a lock across all of the readers, then you might have some undesired behavior there as well.
Yeah, that wouldn't be a good idea.
Yeah.
For exactly that reason, you wouldn't know when to release the lock.
Yep. Right. All right. So that's sort of one characterization of what you might want reader to have, what behaviors. Another thing that the paper, so this sort of has positive requirements, like certain things must appear in the directory, may appear, presumably unstated, but there is that if a file just wasn't there, wasn't created, wasn't deleted, never existed, probably should never appear in the result of reader. I'm not going to write this down, but I think that's implicitly in the SibylFS developers' heads as well here. One interesting constraint they state in the paper is that same file only appears once. So if you call reader, the same file will not show, the same file name will not show up multiple times in the result of reader. So I think this is basically a hypothesis they state. I don't think it's actually correct for most file system implementations because just to give you a mental model of what happens with reader, the directory is represented as a list of blocks. There's a lot of directory entries here. You might have file A, file X, B, foo, etc. And what opendir does is you get a handle on the first block representing the directory, and reader gives elements out of this directory one by one. So as you call reader. And then when you get to the end of the directory, then you get EOF out of this guy. So with this implementation in mind, you could sort of imagine why it's the case that if you delete a file concurrently, it might or might not appear. It sort of depends on whether this file was already past the point where you were reading or it has yet to come. But I think actually it's possible for the same file to appear lots of times, because what could happen is that maybe you saw file B, so that was returned by reader. At that point, file B was deleted by someone, and then it was created, but then the implementation put the file B record over here. So then when you step and you call reader again, you get B a second time. So I think their spec is actually a little bit too strict even for reader. I think on a Linux system, for example, if you have concurrent reads from a directory and lots of creates and deletes, you could have the same file name show up multiple times as a result. Make sense? Questions about this reader model that they're talking about? So how do they actually represent this model? So what is a spec description of this bizarre behavior, or like this extremely non-deterministic behavior? So the way they try to capture it is that every open directory actually corresponds to two sets. The first is a set of must entries. So these are the entries that have stayed in the directory for the whole duration. So these are the unmodified guys. They must appear in the result. And then there's the may set. And these are the entries that concurrently were created or deleted. So when you call opendir, this model of a directory is initialized to contain everything in the must set. And then as you read stuff, you just delete it from the must set. But if a concurrent operation creates or deletes a file, it'll stick it in the may set and maybe delete it from the must set if it was already in the must set. So this is a way of representing the reader specification in their sort of modeling framework, because you need some kind of an abstract state and some description of what it means for reader to return an element out of this model. So one question you might have in mind is like, what is the value of this stuff? This seems like an extremely complicated spec that talks about all kinds of concurrent behavior, whereas the implementation sketch that I gave here might actually seem much more concrete and much more precise and almost easier to understand than this whole notion of must sets and may sets. So why do they need this super complicated model of reader that's way worse than the implementation? We've been talking that the spec should be simpler. Any thoughts? So one possible answer, I think that's like maybe easier to see, is that the usual answer is to check many implementations, of course, in some sense, because implementations might differ in exactly their behavior for this reader operations. But maybe the more interesting way to look at this is that it really captures the core of reader that developers can rely on. And here, I mean application developers, not file system developers. So the way to think of this is that suppose you want to write a portable application piece of code that's going to run on Unix machines, but you don't know which Unix machine or which version or which file system. You want to use reader. And you're trying to figure out, how can I use this correctly? How can a different Unix variant cause my application to break, and how do I avoid that? So this formulation might actually help you as an app developer to figure out what is it that you should expect from reader across the board on any Unix machine versus what might be a bad assumption because it only works on Linux and not on macOS. So I think this is the sort of maybe almost the more valuable way to think of why this spec is useful, is that it really helps the app developer understand what they can and cannot expect in the general case from this operation. Any questions about this stuff? Reasonably clear? All right. So I guess another thing that I wanted to cover now is to talk about how exactly they model this file system in SibylFS. So we looked just now at a small fragment of how they model the directory state for the purposes of reader. But more generally, we can talk about how does SibylFS actually capture the entire file system state. And here the paper is actually very pleasantly, very concrete and easy to understand in some ways. So they actually say, well, they define these labels. And the labels, as we were sort of talking about, are basically for them 5 types, which I think is mostly for their convenience. So there's a system call label that says, I'm invoking a system call. So something like a call, and it takes a PID as an argument that describes which process is invoking the system call, and the actual command. And this command, this thing, is actually the syscall name and the arguments that are being passed to the system call. And they also have a similar system call return operation that says, here's a PID that just returned from a system call, and here's the value or result of that system call. Let me restore my crashed application here. So the outcome of the syscall might be some sort of a value here. Always restores with a different color. It's puzzling. So after you return from a system call, you get some sort of a return value back. And then they have sort of separate syscalls or separate labels for creating a process and destroying a process. They also model user IDs and group IDs, but that's not super relevant here. You could think of them as really system calls, but I think for their purposes, it's easier if they were significantly different because they behave quite differently to file system operation, because these guys actually modify the set of processes running on the machine. And then they have this tau transition, which is this interesting transition that allows them to deal with concurrency between processes. So the problem that this tau transition solves for them is that it allows them to reorder the execution of system calls. So suppose that at the implementation level, what happened is that, so here's the code level execution. You had one process that maybe called rename in PID2. And then before that system call even had a chance to return, you called unlink from PID3. And then you got return values back. So now you have some return for process 2, and then some other kind of a return from process 3. And the question is, how do you model this execution at the spec level? At what point did the system call actually take place? So did the rename happen before the unlink, or did the unlink happen first? So if you model only transitions that are either syscalls or return values, then you basically are going to couple the execution of the system call, the actual rename or the actual unlink, together with this label transition. So then, for example, if we were to write our transition function to emit the syscall label at the same time that it actually executes the syscall, then the execution of the rename must happen before the unlink, because here, the rename happens first. Similarly, if we couple the actual execution, the change of the spec level state, to when the return label gets emitted, then this also pins down, the second one returned first. But what this tau transition allows us to do is to sort of decouple them. So we'll have one transition that takes the rename at the spec level, and then we'll take the unlink. But all these transitions do is they don't actually execute the rename or the unlink. They just save the syscall that this process wants to do inside of our spec level state. And by saving the syscall, we sort of accept the syscall arguments from the application, but we don't commit ourselves to executing them in any particular way. So then we can execute a tau transition for process 3 maybe first, and then we'll execute this tau transition for process 2. The tau is when the syscall actually runs, and then we can then, as a third step, return them in any order we want. So as you can see here, we're able to model the situation where the rename and unlink were concurrent. The rename went in first and got its return value first, but actually executed second because of this tau transition that went after PID 3. So this tau transition is how they're able to represent uncertainty or non-determinism with respect to the order of concurrent system calls. Now, each system call itself is an atomic step. So the rename executes all at once, before or after the unlink, but at least this tau allows them to order them in different ways. Make sense? So this is how they deal with the labels and the transitions, and this helps them deal with concurrency. And then the state itself, the OS state from the paper, is actually not too surprising. There's basically a table of all the open file descriptors. It looks like a map, like you would see in any other programming language, almost. There's a table of currently running processes that's indexed by the process ID. And then this is sort of the ephemeral state, if you will. This represents the state of currently running processes and the files they have open. And this is the process state. And then there's the file system state, which consists of the directories that exist and the files that exist in the file system. And then once they have defined these labels in the state, they basically write this function called OS_trans. And this guy basically is a function that takes one of these OS states in. And it's kind of a relation that says, well, here's a label that we're going to produce, and here's a set of OS states. This is the multiple states that we talked about before. Or there's some kind of a special state here. And this special state captures things that the POSIX talks about as being undefined behavior or unspecified behavior, etc. So this is some kind of a special token saying you entered an unknown world as far as POSIX is concerned, undefined. But that's sort of how they model, how they represent the possible executions in their LEM language by basically modeling the state, the labels, and then this transition function. This transition function, actually, they make a big deal out of the complexity and how to deal with the complex thing, but as far as I can tell, it's actually fairly standard software engineering ideas there, where they basically, in the definition of this guy, they use function calls. So they have, smaller functions in LEM for dealing with things like, path lookup, or operations on files, or file operations, or process operations. And they just compose these function calls very much like you would write a piece of software that one function calls another. So it seems like a good idea. And the cool thing is that LEM supports this, and they have their triple pipe combinator for composing them in a non-deterministic way. Make sense? So that's most of their story. They have actually reasonably interesting results where they actually found bugs in POSIX and implementation bugs, as well as sort of interesting invariant violations. but maybe the high-level bit, it actually is find surprisingly few bugs. Actually, file systems seem to be pretty good. The bugs that they report seem to be mostly corner cases, although they find like 2 or 3 serious bugs that seem like they could maybe cause some damage. All right. Any questions about this SibylFS paper? Hopefully, it's a reasonably concrete thing that we've looked at, how to actually specify a sophisticated system in practice. All right, if there's no other questions, I think that's it for this lecture. Next week, we're going to look at separation logic, which is a pretty powerful technique for reasoning about different parts of your system state and simplifying your specs. And then we'll talk about a verified file system that actually tries to prove that a file system implementation always meets a spec. The spec there is a little bit less ambitious with this SibylFS thing, but the implementation proof is more ambitious. All right, so we'll see you guys next week. If you want, feel free to stick around and ask more, individual questions if you want. But otherwise, see you guys.